Okay, I am Mark Miller of Agoric, telling you about our approach to programming secure smart contracts. As we've seen, people trying to program smart contracts have been making extremely expensive errors, and been making those extremely expensive errors, including by the real experts who've taken a lot of care trying to program them well. So programming smart contracts securely in the way the industry is doing it now is just too hard and too hazard prone, and the losses are too great. So we have a different way. I'm going to take you up several levels of abstraction. The first one is machines. We're all building on top of computers. Each of these individual planes is a physical machine, but the stacking indicates something else. From our perspective, a blockchain is really just a logical machine. It's a machine that's built out of agreement between a massive number of physical machines, but logically, in terms of programming it, we see it as a machine. The solo machine is actually just a physical machine. It's conventional. And then the quorum machines are where you have moderate replication, still to give rise to a logical machine. Those would be like permission quorum mechanisms like Hyperledger. So what we want to do is build a level of abstraction across all of these. We want to treat each of these machines, whether they're solo machines, quorums, or chains, as nodes in a cryptographic distributed system. So we're building a cryptographic protocol by which these things can communicate with each other. So the next level of abstraction up is what we call the VAT layer, where each of these green boxes is a VAT. It's a process-like unit. And these VATs speak to each other with cryptographic messages in ways that authenticate who sent the message. And on top of that, we build a system of distributed secure objects, sending messages to each other, where the one object can send a message to another, whether the other object is in the same VAT or a different VAT, or whether the other object is in a VAT on a different machine as well. That we have a uniform fabric of objects sending messages to each other. And this is in the object capability paradigm, which is what the OCAP stands for. We're actually doing this in an object capability subset of JavaScript. I've been on the committee now, the ECMAScript committee, for 10 years, helping fashion JavaScript into a language that can support this. And then finally, on top of that, we have our actual smart contract layer. By building up to first having a clean layer of secure distributed objects, we now have a basis for building electronic rights and smart contracts in a much simpler and more confident manner, and in a manner that can be made accessible to many more non-expert programmers. And what's particularly interesting, I want to call your attention to the smart contracts and e-rights in a loop over there. E-rights are electronic rights. Smart contracts manipulate rights. But smart contracts, in manipulating rights, themselves create new rights. And the new rights that they create can in turn be manipulated by smart contracts. So this gives rise to a new pattern of contracting that we refer to as higher order contracting, by analogy to the notion of higher order programming in conventional programming languages. Our system comes in 3 protocol layers. VATTP is the protocol that builds the VAT level of abstraction out of the machine level of abstraction. CAPTP, for Capability Transport Protocol, builds the OCAP level of abstraction out of the VAT level of abstraction. And then ERTP, the Electronic Rights Transfer Protocol, builds the rights and contracting level of abstraction out of the object level of abstraction. So let's start with the world of objects. And first we're going to work our way down. That'll be the first part of the talk. Then I'll break for questions for a while. Then we'll come back and do the final part of the talk back at the E-rights layer. So the basic step of object-oriented programming is when object Alice says, for example, bob.foo of Carol, invoking the bob's foo method with Carol as an argument. So the thin arrows represent object references. And what's shown here is that if object Alice already has a reference to Bob and already has a reference to Carol, then Alice can invoke Bob with that reference. The thing that makes to get from objects to object capabilities, we only need to impose some restrictions that are very natural restrictions from the point of view of the object program. That these references that carry messages, that those references are the only thing that carries causality. So one object can affect another only by invoking its public interface, and an object can only affect the world outside of itself according to the references that it holds. And the references it holds, as we see here, it can also pass. So the result is that references are the only representation of permission. That means that the reference graph from the programming language literature becomes identical to the access graph in the access control literature. And that means that the natural expressivity of object-oriented programming patterns we can now leverage for the expression of rich security patterns, including electronic rights and smart contracting. But this dot here creates a problem. This dot is the immediate control return control flow, where Alice is invoking Bob right now, does a control transfer to Bob, Bob executes to completion, returns to Alice. And everything that Bob does while it's invoked is part of Alice's transaction. And because Alice is suspended, Bob could call back into Alice, even though Alice might be juggling a bunch of state, is in a delicate situation. But Bob calling back into Alice in that situation creates reentrancy hazards, such as the Dow bug was an example of that kind of synchronous callback while a caller had various state in the air. So this kind of synchronous interaction is only appropriate locally, only appropriate if Alice and Bob are co-located in the same vat. We introduce this infix bang operator, the eventual send operator, that does an asynchronous invocation. Sends the message foo to Bob eventually to be delivered to Bob in a separate transaction. And when Alice sends that message off, the message send immediately returns to Alice a promise for what the result will be. And now Alice and Bob are protected from each other. Alice's transaction completes without being affected at all by Bob's activities in reaction to the message. And likewise, when Bob receives the message, that starts a new transaction. So you have nice temporal isolation, keeping them from disrupting each other. So now Bob can be local or remote. Alice doesn't have to care where Bob is. It's the same programming paradigm.
Questions?
I'm sorry, what?
So it's promise. Is that a promise as to the actual value of the result, or a promise that there will be a result?
It's an object that we refer to as a promise that that is used to designate what the value will be. At some future time, when the value is determined, that object, the promise, actually does designate the value at that time. The cool thing about a promise is the same eventual send can be done on the promise. So if for example, in this example, if Bob here is itself a promise for the result of a previous operation, then the foo message actually gets queued in the promise, waiting for the promise to get resolved. And once the promise is resolved, it then gets forwarded further to the resolution. So as you do eventual sends, you get promises on which you can do further eventual sends. And the promise abstraction we're using here is based on the promises in JavaScript, which are themselves actually based on the promises in my earlier E language, which was designed specifically to have the security properties needed to support smart contracts.
So you can give another question? So
Yeah.
you have some kind of result in the end, and how do you know that you actually got the result? Do you poll, or is it a poll? Yeah.
Great question. Can you repeat the question? The question is, how do you know you got a result back? So there's essentially two fundamental operations you can do with the promise. You can do this eventual send, which just pushes new things in, doesn't ever tell you what you got back. And then there's another operation that there will be an example of later. It's not an example I emphasize, so I'll just tell you about it right now. There's an operation called then. So you say to a promise, .then, and then you give two callback arguments. One callback is the success callback, the other is the failure callback. So if Bob, when he receives this message, if his transaction aborts with an error, then the promise for the result becomes a rejected promise. If the operation returns a value, let's say the number 8, then the promise becomes fulfilled with 8. If you do a .then on a promise with the two callbacks, if it gets fulfilled with 8, then the success callback gets invoked with 8. If it gets rejected with an error, then the failure callback gets called with the error.
Okay. So it's similar to how Java is structured right now. Like, I think recently, JDK APIs are structured.
So I don't know the Java promises. I stopped using Java before they got promises.
Okay.
But what I'm describing is a very direct extension of the JavaScript promises in order to extend them into having the functionality of the full E promises that the JavaScript promises are based on. Okay. So once we can message across machines, once each of these objects might be in a different machine, there are 5 different ways in which this simple diagram can be cut between machines. So let's focus in on the most interesting one, which is the one at the bottom. So here, Alice still thinks she has a reference to Bob. Each VAT is now divided into 2 portions. Local SES. SES is secure ECMAScript. It's the object capability subset of JavaScript that we've created. And then CapTP surrounds it. That's the serialization unserialization layer. All of the application, the normal application programmer, all of the objects they're normally concerned with are just the ones that live inside the respective SES boxes. All of the rest of this is just the infrastructure that makes it work so their messages can get from one object to another. This CapTP level, in order to do the serialization between these VATs, needs 4 tables. It needs a table in each direction between a pair of VATs. But these arrows are really way too large to work with, so let's trim down the graphic. But I showed you the arrows in order to have a mnemonic when you look at this graphic as to what the directionality is. So these tables are import-export tables, and they're matched. When VAT B and VAT C get connected, There will also be import-export tables between that pair. I'm showing also within VATC these two additional tables, the handoff tables, which I'll explain in a moment. But first, the export tables. Computation in a blockchain cannot keep secrets. So we had to reformulate a lot of how we're doing things so that all of the access control, all of the distributed security could work without depending on transmitted secrets and without having the object computation at the endpoints internally have to have secrets. So so Bob being entered into the export table that A can use when a message comes in to VAT B from VAT A, the fact that it's authenticated as being from VAT A is the thing that lets VAT B know that message can address that table. So the index in that table, which is matched between A and B, is how VAT A talks to VAT B about Bob. VAT C can't currently access Bob because Bob is not exported through the export table that VAT C can access. And then the handoff tables have a particularly restrictive rule, which is VAT C's handoff table from A to B is one where only VAT A can instruct VAT C as to what to place into the table, and only VAT B can instruct VAT C as to what to take out of that table. That's the A to B table on the left. So when Alice sends that message to Bob, what she's really doing at the object level is sending it to a local proxy for Bob that has to serialize the message. The first step of that serialization is that VAT A sends to VAT B a give to message. VAT A is essentially saying to VAT C, when VAT B asks you for an index, the Carol A to B is just an index that VAT A made up. When VAT B asks you for that, give it Carol. And the message talks about Carol by using the index in the export table that VAT C, of the things VAT C has exported to VAT A. And having serialized that message to eventually be delivered to VAT C, VAT A can now complete serializing and sending the foo message, saying to VAT B, please ask VAT C for what I left for you at the Carol A to B index, and deliver the foo message to Bob with that argument. So when that message arrives at VAT B, and VAT B proceeds to unserialize it, the first step in the unserialization is sending a corresponding take from to VAT C, saying, asking, what did VAT A leave for me at Carol A to B? And having sent this message off, even though it has not arrived yet, sending the message off leaves behind that little half circle, which is a promise for what the result of the take from will be. And now that the promise for the result exists, VAT B can complete unserializing the message into an object message, which it then delivers to Bob. And now Bob has the promise for the result. Bob can continue computing, even though none of these messages for VAT C have actually reached VAT C yet. VAT C, in fact, could be offline with all these messages just accumulating in some store and forward infrastructure somewhere. Now, this red line that I have not explained is a happened before constraint. It's something that was propagated through the protocol where the take from message records that the give to message must be delivered to VAT C and such that VAT C can operate on that before it sees the take from message. And so we now know that the give to will arrive first. There's redundant paths by which it might arrive, but when it arrives, VAT C acts on the give to by placing a pointer to Carol in that table at the index that VAT-B expects. When the take from arrive message happens, the reference is taken and it's placed in the export table at an index that matches the index in the import table that the promise was already registered in. Now, in our crypto world, of course, our crypto multi-machine world, there's a lot more going on than just serialization and unserialization. There's also encryption and decryption and signing and signature verification and a whole routing fabric standing between these machines to get messages from one to the other. And the overall flow is that when Alice sends an object message, it lands in CAPTP that has to serialize it, delivers it as a serialized blob to VATTP, that encrypts it, sends it over the network to the other side's VATTP that decrypts it into a binary blob that needs to be unserialized into an object message and delivered to Bob. Now, another important element of making this work is there's this non-deterministic merge, which we can think of as like a traffic merge, where multiple lanes have to come together into one lane. What the overall order is of how the multiple lanes arrive at one lane is non-deterministic. There's multiple possible orders. But that's where fundamental non-deterministic choice has to happen, which is that as the messages come in, they must be delivered into the object world in some specific full order. And this was the state of our thinking until the alien Satoshi Nakamoto visited our world and gave us new insight that changed everything. So to explain how this whole picture lifts to ride on top of blockchains, I'm first going to take us through the milder step of quorum VATs, of VATs running on quorum machines. So over here, VAT-B is a 2 out of 3 quorum. Each layer of VAT-B is a separate physical machine. Each of those physical machines can be separately owned, can be in different administrative domains, separately trusted or not trusted, and crucially, in different jurisdictions so they're not subject to the whims of any one government. And the definition of VAT-B is the enumeration of the 3 participants and the thresholding rule that anything the 2 out of 3 of them agreed on is, by definition, what it is that VAT-B did. And likewise, VAT-C at the bottom is a 2 out of 2 VAT, so it only proceeds with unanimity. And VAT-A, showing it as a 1 out of 1 VAT, is really just the same old degenerate case of just a solo machine. Now,
So one
yeah.
of the conditions probably there is no kind of network partition, right?
So the network partition. So if there's a network partition, then the side of the partition in which there are participants, if any, in which there are participants that are able to meet the threshold, on that side of the partition, the VAT can continue to move forward. And other things on that side of the partition can see. Outside the partition, if you can't receive message from the threshold quorum of participants in the VAT, you cannot see progress. Now, when you get into massive multi-way replication, then you have a lot of the high availability properties that we're used to for blockchains. So at this level, with regard to the individual VATs, nothing we're saying changes the availability characteristics of the partition. It's just sort of standard form issues with regard to partition. With our fabric going between them, the fact that the messages are individually signed and can be delivered later means that if there is a partition, traffic can just accumulate to be delivered later when the partition heals. So, so that means that there's not necessarily a logical disruption, and you can still use replication to get higher availability, but subject to all the normal, distributed computing theory constraints on making progress on the partition. Okay. Now, once we have multiple layers, the merge now becomes more interesting because, as I mentioned, the merge is doing a non-deterministic choice. In all other ways, these three layers can be proceeding independently, but all three layers have to make the same non-deterministic choice to arrive at the same arrival order of messages. So instead of a separate merge per layer, there's a consensus box that cuts through all of the layers, and that's the essential place where all of the layers need to coordinate with each other in order to come up with the overall agreed order. So as the messages arrive individually from other VATs and they arrive individually from different layers, they accumulated the consensus box until the consensus box can make a joint decision across all of these layers about one order. And when it does make that decision, then the consequence of that is emitted simultaneously to all three layers. So all three layers are like a triple-decker bus of messages. So all three layers see exactly the same incoming order of messages. And that's good because the three green layers, they're doing the same kind of job, but they don't need to do it in sync. The three blue layers have to be exactly, perfectly in sync, because that's where the validation comes in, that they're reproducing exactly the same computation. Yeah?
Does the 2 out of 3 rule apply in case of a network partition to the consensus as well?
So the consensus, the answer is probably yes. The reason I say probably is I want to say that in defining a VAT, there are two separate policy issues that you can make separately. One is for somebody outside the VAT deciding whether the VAT said something, what threshold they should use, and then there's, within the consensus mechanism of the VAT, what consensus rule should be used. And those can use different thresholds. Those don't need to be coupled. But often, you'll be making the same decision across both. Yeah.
So this question is about ordering by what? By timestamp, by median timestamp.
So at the when the serialized message is emitted from CAPTP and handed to VATTP, it says what earlier messages must be delivered ahead of it. And it actually includes those, it includes the, I'm going to just speak in first approximation. We can come back to it during the QA period. The short answer is it includes those earlier messages, like the take from includes the give to. Basically, as a certificate change. So VAT A tried to send the give to VAT C, but then it also included the give to as an opaque payload that got carried so that when the take from went to VAT C, it also carried the give to just in case so that it could be, to ensure that it got delivered earlier. But the key thing is that logically every message says what is the tail of the causality chain of messages that must be delivered ahead of that one. So every message has a cumulative hash of the tree of earlier messages. And that way you ensure that a message does not get honored unless all of the earlier messages needed to show that the cumulative hash is correct. Until you see that cumulative hash validate, you don't honor the message. So at every level of abstraction here, there are adapters, and the adapters each have their own tables. The red adapters might be routing tables in network fabric, or a distributed hash table, or whatever. That's the last we're gonna mention the routing fabric. We're going to focus in on the green adapters, which are cryptographically how one VAT talks to another. So when Object Alice sends that foo message, we've already seen that the consequence of sending that foo message is that the CAPTP level sends two serialized messages to VATTP. It sends a message from A to C, and it sends a message from A to B. And the message from A to B, this will help answer those questions. The message from A to B records that it must come after the message from A to C. And then, as the messages are sent, they're sent through this. In the top, there's a 1 to 3 fan-out multicast device. Facing that C, there's a 1 to 2 multicast device. And that's because the outgoing message has to be delivered to each of the hosts of that VAT. So let's say that the messages from A to B, the A to B arrive first. And now they've arrived at the quorum mechanism as candidate messages to be delivered next. Let's say that they're accepted. The top host, the B computation, calculates that outgoing message that gets similarly hits the fan-out device. But now, this is the first time that VAT B has heard of VAT C, so this is when it builds those tables. It then contacts VAT C, which is the first time VAT C has heard of VAT B. So at that point, VAT C constructs the corresponding tables. And then the message gets multicast to both of the hosts of VAT C into the incoming 3-to-1 fan-in device, which is the thing that gathers evidence towards the hypothesis that the VAT as a whole said something. Seeing that one of the hosts contributing to VAT B claimed that it said something is evidence that VAT B said something, but it's not definitive evidence, not conclusive. So that message is stuck there, waiting for more evidence. However, the A to C message being emitted from VAT A needs no further evidence. So being carried along, it can just go ahead and get sent to the first host of VAT C. And then likewise, the other part of multicast from B1 to C carries through the rest of it. It gets delivered to the quorum mechanism and processed. So now that that message has been safely processed, we still have 2 stuck messages. And that's because only one of the 3 B hosts has actually done the computation. So let's say that B2 proceeds, sends the same message into the fan-out device at its layer. And now, one of the places it gets multicast is the first host of VAT C that now has 2 out of 3 evidence, which by the definition of VAT B is adequate evidence. So at this point, that fan-in device can release the message, and it's now a message that's taken to be from that B as a whole. But still just delivered to the first host of that C. But then, of course, the other one likewise delivers it. Now they make it through the consensus mechanism, and we have our capability finally all put together, going from Bob to Carol.
So just to understand this.
Yeah.
So you're saying when I'm communicating and receiving messages from some VAT, I need to know what is the internal structure of that.
Yes.
How many layers?
Not the internal structure. You need to know what, as a matter of fact, that's the perfect segue for this slide. So it's like the perfect question. So it's the definition of the VAT is explaining how to talk to it. And so when you learn the name of the VAT, you know what devices to build in order to talk to the VAT. So this is a special case of a very general technique that is sometimes referred to as self-authenticating designators. Things whose name explains to someone holding the name what decision procedure to use to determine if a particular thing is the thing that the name designates. So the most familiar example of this is a cryptographic hash. So when you just have a snapshot of data, if you name the data with the hash of the data, which all of the systems shown in the parens there do, then anyone knowing that name knows what to do when presented with data that is allegedly the data named by that name, which is the hashing. So more generally, the name explains a decision procedure to the entity holding the name as to how it is they should figure out how to authentically deal with what the name designates. So with the VAT ID, the VAT is not data, it's an active computational entity. So the problem we have to solve is somewhat different. There's two subproblems. My name has to explain how to talk to me, and my name has to explain how to listen to me. So on the talking, it's cryptographically how to send me messages that I'll recognize, where to deliver them, routing information, etc., and multicast as we've seen if necessary. And then how to listen to me, how to tell if something that I've allegedly said should in fact be treated as something I've actually said. So in the history of this model of computation, which goes back a very long ways, goes back to the mid-90s actually, all of those previous systems were using live TLS connections. And a live TLS connection, because of its symmetry, because of its bidirectionality, it solves the whole problem for both sides in one mechanism. But exactly because of its one-for-one live connection nature, it doesn't generalize into the world we're trying to build. So instead, we sign individual messages. Each individual message can be treated as a unit, and now we can accommodate store and forward VATs. As we've seen, a quorum VAT the name of the quorum VAT can list the public keys of the participants, the hosts that are contributing, and can state the threshold rule. Any 2 out of 3 of these enumerated participants are what it means for this VAT to have done something. That's the meaning, that's the name of the VAT, is the authenticity rule. And then, of course, that's a step towards blockchains. The device you have to construct for talking to a blockchain is essentially a light client, for whatever the light client is, for sending messages into that blockchain. And that's very nice because it's light. Unfortunately, to really listen to a blockchain securely and determine what it said in a definitive manner, the listening device has to be more like a full node, and for blockchains like Ethereum that don't have finality, you have to, in particular, build in front of it a finality thresholding, and that's heavy, and I won't be saying anything more about finality thresholding today, but there is an expense in interfacing this to full chains. So that's the end of part one. We've gone through these three layers. Next, we're going to talk about the actual smart contracting layer now that we have the foundations. We understand why distributed secure objects can work across the whole system. So if anybody has further questions they'd like to ask here. Yes, please. Okay, yes.
Does everything work with the virtual environments, containers, and all that stuff when we talk about machines?
Yeah, so one of the interesting things about a VAT, which I didn't mention, is that the VAT is also the unit of portability, the unit of migration. And when you migrate a VAT, the blue level is the thing that you have to snapshot and migrate. The green level, you have to rebuild a new one around the blue level because that's very dependent on where the VAT is, both what it's being hosted on, as well as from there how it talks to the other things it talks to. But the fact that the blue layer can be snapshotted, moved, and reconstituted is really very, very cool. And because of the store and forward nature of the messages, once it's revived, the old messages that are outstanding to it, assuming that they get routed correctly, the underlying object message within those messages does get delivered, and computation just continues transparently after the migration. Okay, so.
I have another question. Do you have
Yeah.
just basically tools which you use to verify, kind of security flaws in smart contracts?
Yes. The question is, do we have tools that we use to verify security properties of smart contracts? So the answer yes is premature. This is a long-term activity, but we have been collaborating with some academic formal methods researchers now for several years. The closest collaboration is with, I'll just name drop, Sophia Drosopoulou of Imperial College, James Noble of New Zealand, and Toby Murray of the SEL4 Data 61. The four of us together have been working on a specification language named Chainmail that you'll see a little bit of in a few slides. And we've been doing hand proofs of verification that the code, essentially very similar to the code you're about to see, we've been doing hand proofs that that code satisfies the formal specification. And we've been trying to only make hand-proof steps that we believe can be automated. But the formal methods work just takes a long time. So even though we've been working on that for years, it's going to be a while before that gives us any kind of tooling for formal verification. However, the really important thing for the present is that the activity of working on that, on the side, ensures that the semantics of the rest of our system stay clear and simple. It ensures that we don't confuse ourselves because the formal methods work will highlight if we've accidentally introduced something that's a nightmare to formalize. So now we're going to focus in on the E-rights and smart contract analysis. So we've already seen OCAPs, object references being permissions. Well, permission to invoke an object is a kind of right. So, so when we talk about building E-rights on top of OCAPs, what's the difference in the kind of right that we would build as opposed to the kind of right we already have? We're going to be building the new ones as a pattern on top of the old ones, but the new ones have their own character. So on the left, Alice is just invoking Bob, passing a reference to object Carol. On the right, Alice is paying Bob, over here shown with bars of gold. So the first difference is shared versus exclusive. And this is the remaining line from Alice to Carol on the left. Shows that even after Alice has passed the message to Bob, Alice could have still held on to it. And even if Alice didn't hold on to it, Bob has no way of knowing that, so Bob must conservatively assume that she did hold on to it. Whereas on the right, Bob does not consider himself to have been paid unless he knows that he has exclusive access to the gold, unless he knows that Alice no longer has the gold. There's exercise versus symbolic. Objects are all about the exercise right. You exercise a right when you actually do something with the right, like invoke the object provoking its behavior. Whereas money is just symbolic. It doesn't do anything. It's only valuable because of the expectation that you can trade it to others who will in turn value it. An object, by default, is opaque. When Bob receives the Carol argument, he's just received some object from someone who could send him messages. He doesn't know what the object is. He can provoke its behavior, but he doesn't know what behavior, doesn't necessarily know what behavior to expect. It requires more patterns for Bob to be able to form such expectation. Whereas on the right, again, Bob doesn't consider himself to be paid unless he knows what it is that he's gotten, what it is that he's received the exclusive right to. And then there's specific versus fungible. Each object is unique, whereas the money is just a quantity. Bob doesn't care about one bar of gold versus another, he just cares about the total quantity. Now, it's not that E-rights represent just the right-hand side, but just the right-hand column. OCAPs represent just the left-hand column. That part's true. But this contrast is showing us a taxonomy with multiple dimensions. And we want a language for talking about electronic rights that covers all the dimensions of variation described by this taxonomy. So this is the age-old mint maker example that's been repeated in the object capability community now for at least 20 years. And the beautiful thing about this example with regard to the taxonomy you just saw is that this is all of the code needed to build rights that have all of the attributes we saw in the right-hand column out of object capability that have the attributes in the left-hand column. So this code establishes or demonstrates that object capabilities are a good foundation such that the entire rest of the taxonomy can be easily built by patterns with the object capability foundation. So using that purse example, Alice would have a purse with gold in it. Bob would have his own purse with gold in it. We're going to remove the gold bars from the diagram for the moment to be clear. And Alice would send a buy message to Bob if she wants to, let's say, buy tickets from him. When Bob gets the buy message, at this point, all he knows is he received an alleged payment, but he sends to his main purse this deposit method, and when the deposit method acknowledges that the deposit was good, Bob now knows he's been paid without trusting Alice and can release the concert ticket. This fully protects Bob from Alice, but it does not protect Alice from Bob. Bob could just pocket Alice's money and then not give a concert ticket in exchange. So what we need, in addition to the taxonomy of rights that include these 4 dimensions, is we need somehow to build one more element, which is all or nothing exchange of rights. On the left, for object computation, an object message is one way. That's the normal, useful way to do object computation. On the right, smart contracts are generally about the exchange of rights. We need to know that both parties have received the rights that they were looking for, that they were expecting in exchange for the rights they were offering, and otherwise that nothing happens. Either both parties are satisfied, or everything is unwound and it's as if the exchange was never tried in the first place. So this is a portion of chainmail, the formal specification language. It's not much of a portion of chainmail. I refer you to the papers you can find linked off of agoric.com for more on an earlier version of chainmail. But this portion of chainmail shows the elements of ERTP, the Electronic Rights Transfer Protocol, which basically consists of 3 object interfaces that are related to each other, each of which have a set of methods, define a set of methods. So the purse is the thing that we're doing the deposit to. So that's the deposit method we see over there. A particular, in order to bring about the exclusive transfer, what we need to do is reconstruct that purse example as rights implementing this abstract interface. And the key thing about this abstract interface is that rights across the entire taxonomy, including especially the attributes of exclusivity and the attributes of assay, being able to know what it is you've gotten, rights across that taxonomy can all be implemented in such a way that they're described by the ERTP protocol. And the ERTP protocol, this set of object interfaces, now enables us to build, and this over here, this is actually the reconstruction of the purse implementation. It's a little bit more code, not a frightening amount of more code, in order to take the same logic and embed it in this very general description of ERTP. And the result of doing that is we can now create generically parameterizable contracts. Contracts like an escrow exchange contract that handle any right that is presented through the ERTP protocol. So this one contract will deal with rights across that whole taxonomy as long as they're packaged in objects that implement the ERTP protocol. And the escrow exchange in particular, for Alice's gold, for Bob's concert tickets, is basically the code that you just saw is essentially a 2-phase commit among mutually suspicious parties using ERTP to manipulate the underlying assets. So that's the escrow exchange contract. And we'll see this pattern of 5 players a lot. There's the issuer of one of the goods being traded, the issuer of the other good. There's the contract in the middle, and then there are the players. Another example is a covered call option. Let's say that that Bob offers Alice, well, I'm going to hold the ticket in reserve for you. You can buy it any time within the next week. This is very much like an escrow exchange, except that Bob's tickets are pre-escrowed, and Bob has lost the ability to cancel before the deadline. In the escrow exchange, Alice and Bob could cancel at any time. The covered call is built out of the escrow exchange primarily by the pre-escrowing of the tickets and by taking the cancel ability and putting it in the game clock rather than giving it to Bob. So until the deadline, Bob cannot cancel. Now, the interesting thing about such contracts is this is a contract that unfolds over time. Any contract that unfolds over time, the ability to play the contract while it is in motion, to play the contract prior to the deadline, is itself valuable. For the next week, Alice could spend the money to buy Bob's concert tickets. But let's say that Alice finds out that she has a conflict and she can't actually go to the concert anyway. Well, the contracting framework that we build around the contracts acts as issuer for the right to play that role in the contract as a right described by ERTP. So if Alice wants to sell the option to get the concert tickets to Fred, she can just use the contracting framework around the covered call as an issuer of the right to participate in the contract as the Alice side of the contract. And that becomes an issuer of ERTP described rights into any further contract that can operate on any ERTP described right. So this is fundamentally powerful in a way that should be familiar to us from our object-oriented and functional programming paradigms, which is we build abstractions for manipulating objects, and then we package those abstractions as objects, which can thereby be manipulated by other objects. And when we create a generically parameterizable abstraction, like a table that you can put any object into and take it back out of, then that becomes higher order. It is itself the kind of thing that it can manipulate. It can manipulate objects irrespective of what other objects those are manipulating. So and it's that higher order nature of functions and objects that leads to the composability that has created the richness of the modern software industry and large, rich frameworks and object-oriented libraries and compositions of them. The compositionality of software is built out of that higher order nature. What we've seen here is a generalization of that from the object rights that are strong on exercise but weak on the other 3 elements of the taxonomy. We've seen a generalization of that higher order composability across the whole taxonomy. A contract that's generically parameterizable over any right implemented by ERTP, by being a contract in the framework, creates ERTP-described rights for participating in the contract, which means that generically parameterizable contracts can manipulate the kinds of rights they create. And we can now create deep compositions through this duality of rights and contracts. We can create deep compositions that are necessary, we believe, for the richness of contracts that we create to be a rich ecosystem of composition that reflects the richness of the market ecosystems in the real world that are inspiring us to set out on this quest. And now I'll take further questions. Yeah.
Maybe it's a silly question, but is there any idea on maybe there should be a limit on the power of smart contracts? So say smart contracts become recursive, they can become impossible to evaluate, or problems like this. Can you repeat the question?
Yeah. Actually, did you want? Were you wanted to do them?
Not working, so yeah.
Oh, okay. I'll just repeat the question. Okay. Should there be a limit? I think you asked a limit on smart contracts, but it sounded from the rest of the question it was you asked really about a limit on the compositionality of smart contracts.
Or their power?
Okay. So in general, my attitude is no, but and I would answer by analogy with object-oriented programming. Objects build on objects without limits, any prior limits on the compositionality, but the result of deep compositions is that some properties can be hard to analyze. And then when you want to be able to analyze certain properties, sometimes you do that by saying, in order to be able to derive certain analysis, to be able to complete certain analysis, I can only complete this analysis on a composite structure that stays within certain bounds, but then that's on a case-by-case basis, depending on what the analysis is. The important thing about the formal methods work that we've been doing is we've been able to analyze these contracts and show that they're correct, that they do the job that we specified, and that they compose with other contracts that we don't need to describe beyond the assumption that they are constrained by object capability rules. And the constraint by object capability rules means that you don't have to reason about their code, you don't have to reason about their behavior. You have to reason about the fact that the limit on their behavior is the capabilities that they've been granted, because the capabilities, the object references, are the only means by which an object gets to cause effects on the world outside of itself. And that's why we're able to do such deep composition with confidence. Yeah?
You had that page where you essentially declared with like kind of an interface
Yeah.
for the implementation you showed in the next slide. But it just sort of seemed like it had some type information. Kind of the things that I would want is like, you had a deposit method. I want to guarantee that a deposit could never reduce the amount of currency in the wallet or something.
Yes, very good.
Yes, do you have something like that? Like
Yeah.
more-
The policy triple dot is actually where most of the specification is. Once again, I'll refer you to our papers and other presentations. And that's, by the way, I should also emphasize, that's still in formulation. We've gone through several generations. Each generation had good formal properties, but there's just a lot of language design on coming up with good specification languages. And it's not just the formal issues on good specification one of the things that we've been very disappointed with, or I personally, let's say, I'll just speak for myself, very disappointed with regard to a lot of other formal methods work, is the specifications themselves are very complicated. They're more complicated than programs that I already have a hard time understanding. And if I can't understand the specification, then we've just moved the problem from what does my program mean into the problem of what does my specification mean. So one of the arts of writing a specification language is that just as we want to program in a way that supports both informal and formal reasoning, we want to formally specify in a way that supports both informal and formal reasoning about the meaning of the specification. And that's where a lot of the iteration comes from. But with regard to the particular example you raised, yes, what our specification is able to specify and what we've been able to prove the purse system obeys is without a purse, you cannot affect its balance. With two purses, you can move money between them, but you cannot affect conservation of currency. With a mint, you can increase the total currency, but you cannot have any other effect on the total amount of currency. And the crucial thing that actually caused a breakthrough in the nature of the specification language to figure out how to really say it in an intuitive manner is that a deposit reporting success means that the invoker of the deposit, Bob depositing Alice's money, that Bob can trust that he has actually received an exclusive on the described amount of money. He can trust that to the same extent that he trusts the purse he deposited it into. So there's this, and that's sort of that turned out to be the crucial lever for this formal reasoning is propagation of contingent trust and suspicion relationships. We don't know if Bob trusts his main purse, but to the degree that he trusts his main purse, he can now then if it reports a success, then he can now trust this other consequence that results from a well-behaved main purse.
So if you're sort of conserving balances and doing something like that, are you using dependent types, or can you talk about sort of? It sounds like the implementation's not done. But
The question is, are we using dependent types? And the answer is no. We are basically starting with just Hoare logic of Hoare triples of, given these preconditions and this thing happens, these are the postconditions. But normal Hoare logic is good for reasoning about sufficient conditions. That if these things, that if you have the following set of conditions, then you expect the following result. They're very bad at reasoning about necessary conditions. Because in order to say, well, if this thing happened, let's say, if the total amount of currency was increased, then somebody must have called the mint. Okay? You can only reason about that in normal Hoare logic by doing an induction over all of the things you've specified. So what we've done is we've extended the Hoare logic to be able to speak compactly about necessary conditions as well as sufficient conditions. We've also added one more clause besides preconditions and postconditions. There's another clause which are the conditions that must be true at every step between entry and exit, the conditions that cannot be violated even momentarily in getting from the entry to the exit. That turned out to, that's not tremendously interesting, but it turned out to really ease a lot of our verification.
and you think when you're done, you'll be able to do that entirely during static analysis, or will you have constraints during runtime that will force these things?
I'm sorry, repeating the question. Thank you for audience signals to repeat the question. Please keep doing that. Do I expect that we'll be able to do this purely with static analysis, or do I expect that there will be a role for extra runtime enforcement? And the answer is mixed. The specification language, chainmail, is purely descriptive. It's reasoning about the program. The chainmail specification does not create any enforcement mechanism. However, in order to have a program that is easier to statically reason about with an out-of-band specification, if the program itself does some enforcement, that enforcement can in turn ease the burden on the specification, and then the tooling eventually can go from the failure to verify to suggested enforcement mechanisms to aid the verification effort. But this is way ahead of where we are right now.
So we have time for about one more question.
Yeah.
Regarding the conditions that must always apply, can you go into a little bit more detail? Because in the deposit case, in traditional applications, you have a moment where you deduct from one account and then you credit to the other account. So in between those two instructions, the condition about the total supply do not apply.
I'm going to answer that question. I'm sorry. Thank you. Boy, that's so hard. In order to transfer money between the purses, there has to be a moment where currency is not conserved. That you have to change one balance before you change the other balance. So how do we write that and ensure that that the way in which it's written cannot cause an observable violation of conservation of currency? So actually, I'm going to go to our current real code. There's no reason for me to use the old code. Okay. So the deposit method, the critical element that I've alluded to, but I haven't really stressed, is that our overall computational model is communicating event loops, where each turn of the event loop is a separate transaction. And the computation that happens during the transaction is simple sequential imperative computation. So there's no fine-grained shared memory multi-threading or anything like that. So the deposit method, between when it enters and when it exits, and might exit either exceptionally or normally, but between when it enters and when it exits, nothing else has any direct access to the synchronous state here. So ledger get purse, that's referring to the ledger, which is the weak map in the upper left. The purses are registered in the ledger on the lower right with the ledger.set. So only purses of this issuer, of this currency, get to be in this ledger. Every time you make a new mint, you make a whole new system of currency with its own ledger. So the ledger.get of purse, well, that's this purse itself, which is defined that their const purse equals def, open paren, open curly, inside make purse. That's the purse that's referring to. So that's my own balance. Nat is a utility function that just checks that the argument has the value of a natural number within the range of safely representable natural numbers. JavaScript will have big ints soon, in which case this first line, the outer nat in this first line will become unnecessary. But right now, the safe range of natural numbers is the a range of floating point numbers. So this first line, the nat on the right is necessary. It's saying, ensure that what I've been handed as an argument is a natural number. The outer nat on the first line is saying, make sure the result of adding these things together does not overflow. That goes away when you have big ints. On the second line, we look up the alleged source purse, the second argument, in the ledger. If the source purse is anything other than a purse of this currency, that lookup fails. And if that lookup fails, then the nat around that fails. It fails with an exception, and you abort at that point. If the lookup succeeds and you have a balance, then you subtract amount from it. You already know amount is a natural number. If the result is not a natural number, then you're overdrawn and you get another exception. Okay. At that point, you've done all of the checks that might fail. And because the remaining part of the transaction has nothing that can fail, it can now do a set of side effects. And because no failure can happen between them, the side effects that remain in the transaction are effectively atomic. They happen before anything else can observe. So it sets the source purse's balance to the decremented balance. It sets this person's balance to the incremented balance. And I will leave as a puzzle for the audience why I recompute on that last line the incremented balance rather than remembering it from the first line. But that's the atomicity issue. But the result is that, yes, momentarily...
You don't check it with NAT, because we should have failed before, right?
So we don't need to recheck it with NAT, but we also need to not reuse the previous sum.
Yeah.
And the reason why we need to not reuse the previous sum, but we're still safe where we don't need a NAT check, is the interesting question that I'll leave as a puzzle for the audience. But the key thing here is that at the granularity of what's observable, which is not this fourth clause that we've added to the Hoare logic, but rather the precondition postconditions, is there is no postcondition of this operation that in which the total amount of currency has changed.
All right. Thank you so much.
You're welcome.
All right. Thanks, everyone. Happy SF Blockchain Week. Hope you're not too exhausted from the